A sudden burst of energy from deep space defies all known physics. These mysterious signals from the cosmos arrive without warning, leaving our most brilliant scientists utterly speechless. In the next few minutes, you will gain a completely new perspective on the universe and our place within it. We will explore transmissions that repeat with strange rhythms and others that vanish without a trace, each one a cosmic riddle waiting to be solved. What do you believe is waiting for us in the vast silence between the stars on a quiet Ohio night in 1977? A radio telescope known as the Big Ear was silently scanning the heavens. Astronomer Jerry Amon was reviewing the printed data, a routine chore of sifting through cosmic static, when his eye caught a sequence of letters and numbers so extraordinary his hand reached for a red pen. He circled the characters 6 in a row, and beside them he wrote a single, powerful word in the margin. Wow! That one word would come to define the most tantalizing signal ever received. For 72 seconds, a narrowband radio burst, billions of times stronger than the background noise, slammed into the telescope. It originated from the direction of the constellation Sagittarius, and its frequency was precisely the hydrogen line, a quiet channel of the universe that scientists had long theorized would be ideal for an interstellar hello. It matched the exact profile of a signal engineered by an intelligent civilization, and then it was gone. Decades of listening have never heard its like again. Some argued it was a passing comet, but that explanation has been heavily debated and fails to account for the signal's perfect, artificial-seeming properties. The WOW signal stands as a ghost in the machine, a one-time event that single-handedly energized the search for extraterrestrial intelligence. It is the benchmark, the mystery against which all others are measured. If a signal that perfect can simply vanish, what other messages might be flickering in and out of existence, waiting for the right moment to be heard? The answer may lie not in a singular shout, but in a signal that repeats with a strange and unpredictable rhythm. While the WOW signal was a solitary, perfect mystery, the cosmos sometimes chooses to repeat itself. Deep within a dwarf galaxy 3 billion light-years from Earth, a series of unimaginably powerful radio waves erupts into the void. They are not a one-time event. They flash again and again, a frantic and persistent beacon in the overwhelming dark. This is FRB 121102, the first repeating fast radio burst ever discovered. Its very existence shattered a fundamental assumption. Astronomers had believed all such bursts were the final, catastrophic death cries of celestial objects, vanishing as quickly as they appeared. But here was a source that lived to scream another day. Scientists like Shami Chatterjee struggled to convey the raw power involved. Each burst, lasting only 1,000th of a second, unleashes as much energy as our sun produces over 80 years. That immense power, concentrated into a blink, points to an environment of almost unimaginable ferocity, likely anchored by a super-dense neutron star or a powerfully magnetized magnetar. The fact that it repeats is a gift to science, allowing telescopes to be trained on its location for prolonged study. These observations reveal the source is embedded in a turbulent, highly magnetized region of space, possibly near a supermassive black hole whose intense gravity could be acting like a cosmic lens, twisting and focusing the signals toward us. This persistent, repeating nature forces a complete rethinking of what could cause such events. A single blast could be explained by a stellar collision or an explosion, but a repeater requires an engine that survives its own violent outbursts, like a pulsar operating at its absolute limit. The discovery of this one repeater hinted at a hidden population, a diverse family of cosmic radio sources, each with its own unique behavior and story. If some signals can repeat with such ferocious regularity, what does it mean when we find a burst that defies not just our expectations of repetition, but our understanding of distance itself, appearing to originate from a place that should be impossible? Years before that repeating signal was found, a single, fleeting event had already been recorded, its true nature completely overlooked. Deep within the archives of the Parkes Radio Telescope in Australia, data from 2001 held a secret. It was a spike of raw energy, a blast so impossibly brief and powerful that when it was first seen, it was dismissed as mere interference, perhaps a glitch from a passing satellite or some earthly machinery. It was filed away as a ghost in the data, an anomaly best forgotten. That changed in 2007 when astronomer Duncan Lorimer and his student David Narkevic re-examined the old records. They found it a pulse lasting just 5 milliseconds, but within that sliver of time was packed an almost unimaginable force, an energy output equal to our entire sun, releasing over an entire month. The key to its origin, however, lay not in its power but in its subtle distortion. The signal was stretched, its higher frequencies arriving slightly before the lower ones. This effect, called dispersion, is the telltale fingerprint of a journey through the ionized gas of intergalactic space. The amount of stretching was immense, indicating this 5-millisecond scream had traveled across billions of light years. This was the Lorimer Burst, the first fast radio burst ever identified. Its confirmation was a seismic event in astronomy. It forced scientists to look back through decades of data with new eyes, searching for other flashes they had mistakenly discarded. An entire new field of transient astronomy was born from that one solitary shout. What could possibly create such a brief yet catastrophic release of energy? Theorists scrambled for answers. Could it be the final, violent merger of two ultra-dense neutron stars? Or perhaps the theoretical evaporation of a tiny, primordial black hole? Some even suggested cosmic strings, defects in the very fabric of space-time. No single explanation has yet emerged as the perfect fit. The Lorimer Burst remains a foundational mystery, a stark lesson that our universe is not a quiet, static place, but a dynamic and violently active arena filled with fleeting whispers of immense power. And if such colossal events can occur in the far reaches of the cosmos, what happens when a similar signal appears to originate not from a distant galaxy, but from disturbingly close to home? But a signal from the cosmic backyard can be the most tantalizing of all. In 2020, the Breakthrough Listen project, a monumental effort to scan the skies for signs of intelligence, recorded something extraordinary. A narrowband signal, christened BLC1, appeared to originate from the direction of Proxima Centauri. This is not a distant galaxy. It is our closest stellar neighbor, a star system just over 4 light-years away that we know hosts a rocky, Earth-sized world within its habitable zone. The signal itself seemed to tick every box on the theoretical checklist for an artificial transmission. It was concentrated into a sliver of the radio spectrum, a focused beam quite unlike the broad, natural emissions from cosmic objects. Even more compelling, it drifted in frequency in a way that perfectly matched the expected motion of a transmitter located on a planet orbiting that star. For a moment, the possibility felt staggeringly close. Lead researcher Andrew Simeon captured the cautious excitement, immediately stressing the need for rigorous verification. The history of SETI is littered with signals that were ultimately traced back to our own technology. And indeed, after months of meticulous analysis, the most likely explanation emerged. BLC1 was probably human-made radio interference, a product of our own increasingly noisy civilization. The investigation itself, however, was a triumph of modern science. It demonstrated a new level of discipline, a step-by-step process to rule out every possible terrestrial source, from satellites to everyday electronics, before even whispering the word alien. This near miss from next door was a powerful drill. It proved our methods are getting sharper and that we are now capable of detecting a signal so seemingly artificial that it passes the first and even the second round of scrutiny. It reminds us that the greatest challenge may not be hearing a signal, but correctly understanding what or who we are actually hearing. If a signal from our backyard can so perfectly mimic an intelligent call, what are we to make of a message that arrives not as a simple tone, but as a complex, repeating pattern of mathematical precision? Sometimes the most compelling signals are not the loudest, but the most persistent. In 2003, a distributed computing project called SETI at Home, which harnessed the spare processing power of millions of personal computers around the globe, flagged something curious. It was a faint radio whisper designated SHGb02+14a. This signal was detected not once but 3 separate times, and it was broadcasting on a frequency very close to 1420 MHz, the universal hydrogen line. This specific frequency is often described as a cosmic watering hole, a quiet channel where an advanced civilization might logically choose to transmit a hello. The signal seemed to drift, its frequency subtly shifting in a way that perfectly matched what you would expect if the transmitter were located on a rapidly spinning planet. All the pieces of the puzzle seemed to fit an intelligent origin, yet the mystery only deepened when astronomers pointed their most powerful telescopes toward the source, a seemingly empty point of space between the constellations Pisces and Aries. The region contained no visible stars, no known planetary systems within 1,000 light-years. There was simply nothing there, at least nothing we could see. It was a whisper from the void. The scientific community was immediately divided. Was this the real deal, a genuine attempt at contact from a civilization orbiting a star so faint we could not detect it? Or was it merely a statistical ghost, with millions of volunteers sifting through an ocean of cosmic noise? The chances of a random fluctuation mimicking an intelligent signal were not zero. Critics argued it was just that, a lucky alignment of background static that happened to look interesting, an artifact of the very distributed process that found it. The case of SHGb02+14a remains in a state of unresolved potential. It is a perfect example of the modern search for extraterrestrial intelligence, an endeavor where citizen scientists can make genuine discoveries, but where the final proof remains maddeningly elusive. It represents the faint, ambiguous whispers that tease us from the edge of detection. But the cosmos is not always so subtle. For every quiet, repeating signal that fades into ambiguity, there is another that arrives with the force of a supernova, a blast of energy so intense it can momentarily overwhelm our ability to even see it. The sheer clarity of that signal was its own kind of message. In 2018, a new era of radio astronomy was dawning with the Australian Square Kilometre Array Pathfinder, a telescope designed to see vast swaths of the sky at once. Almost immediately, it made a record-breaking catch. It detected a fast radio burst of such stunning brilliance and precision that it was pinpointed not just to a general region of space, but directly to a massive galaxy 3.6 billion light-years away. This blast, officially known as FRB 181112, was so impactful it earned a powerful nickname. Its signal was remarkably clean, showing none of the usual scattering or distortion that plagues most bursts as they travel through the murky plasma of intergalactic space. It was as if this particular flash had traveled down a cosmic highway, a relatively clear path through the universe. This precise localization was a gift. For the first time, astronomers like Keith Bannister could look at the burst's home and be certain. They identified its host as an old, massive stellar system, a galaxy where the frenetic pace of star formation had long since settled down. This was a profound surprise. Many scientists had theorized that fast radio bursts must come from young, chaotic galaxies, the kind of environments rich with the neutron stars and magnetars thought to power them. An old, quiet galaxy simply did not fit the script. This single, clean signal forced a complete rethinking of what could create these cosmic flashes. It hinted that the engines behind fast radio bursts are not confined to stellar nurseries. They can exist in stable, ancient neighborhoods, suggesting the phenomenon is far more diverse and perhaps more common than anyone had dared to predict. But the signal's value did not end there. Its pristine quality made it a perfect scientific instrument. Astronomers used it as a cosmic backlight, shining through the faint, invisible material that drifts between galaxies. By analyzing how the clean signal remained clean, they could measure the density and distribution of this missing baryonic matter, the very threads of the cosmic web that have eluded detection for decades. This was no longer just a mysterious explosion. It was a tool, a beacon that illuminated the dark architecture of the universe itself. Yet for every signal that acts as a clear, illuminating tool, there is another that seems to defy the very laws of physics, arriving with a power that theory says should be impossible. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, was not built to hunt for fast radio bursts. Its primary mission was to create a three-dimensional map of the universe by tracking the faint radio whispers of cosmic hydrogen. Yet this revolutionary telescope, with its four massive half-pipe antennas resembling snowboarder ramps, possessed an incredibly wide field of view. It could stare at a huge swath of sky at once, and that made it the perfect net to catch the universe's most fleeting flashes. In August 2018, just as it was beginning its operations, CHIME made a spectacular catch. It detected a source, designated FRB 180814, that did something extraordinary. It flashed not once, but 6 separate times. This was only the second repeating fast radio burst ever identified, and it originated from a staggering 1.5 billion light-years away. The significance went far beyond the repetition itself. When scientists like Deborah Good and her colleagues analyzed the individual bursts, they noticed a peculiar detail. The signals exhibited a distinct downward drift in frequency. It was a cosmic sad trombone effect, where the higher-pitched notes of the burst arrived before the lower ones. This was not the dispersion caused by a long journey through space, but a signature imprinted on the signal at its very source. That downward drift is a crucial clue. It strongly suggests the burst is traveling through an incredibly dense, intensely magnetized plasma. Picture the signal struggling to escape the environment around an ultra-dense object, like a neutron star or a magnetar, where the magnetic fields are so powerful they twist and smear the radio waves as they fight their way out. This single detail paints a vivid picture of the engine's violent neighborhood. Furthermore, the overall dispersion of the signal indicated it had passed through a tremendous amount of material on its way to us, likely within its own host galaxy. Each repetition was not just a repeat performance, it was another chance to study the local environment of the source, to understand the conditions that can trigger such a catastrophic and recurring release of energy. The CHIME repeater and the many others the telescope has since discovered helped solidify a new cosmic taxonomy. It became clear that fast radio bursts are not a single phenomenon. There are at least two distinct classes, the one-off cataclysms and the persistent repeaters, each telling a different story about death and survival in the cosmos. CHIME revealed that repeaters are not rare flukes. The universe is constantly, quietly crackling with these brief, energetic conversations, and we have only just learned how to listen. Yet for every signal that fits into a growing classification, there is one that stands so completely apart it defies all our categories. For years, the search for cosmic signals at Australia's Parkes Observatory was haunted by a persistent ghost. Astronomers dubbed these phantom readings Perytons after the mythical stag that casts a human shadow. They were the ultimate imposters. Each Peryton appeared as a brief, dispersed radio burst, its frequencies perfectly smeared in a way that perfectly mimicked a signal that had journeyed millions of light years through intergalactic plasma. They looked, for all intents and purposes, exactly like the fast radio bursts they were so desperate to find. But there was a deeply puzzling clue. These signals seemed to originate from much closer distances, and they had a peculiar habit of appearing almost exclusively during the daytime and often on weekdays. It was as if the source kept a 9-to-5 schedule. This bizarre pattern pointed overwhelmingly to a local, human-made origin, yet for years the true culprit remained just out of reach. The frustration mounted. Every time a Peryton flashed across their data, it had to be treated as a potential breakthrough, forcing astronomers to waste precious time and resources chasing a ghost in their own backyard. The mystery was finally cracked wide open in 2015, not by looking up at the stars but by looking inside their own break room. The source was a microwave oven. When a staff member impatiently opened the oven door before the timer had finished, the device would release a brief, chirping radio pulse. The massive, sensitive dish of the Parkes telescope, pointing in just the right direction, would catch this tiny domestic burst and record it as a cosmic event. The resolution was both hilarious and humbling. The Great Peryton Mystery, a years-long puzzle that had confounded brilliant minds, was solved by a malfunctioning kitchen appliance. This episode became a legendary cautionary tale in astronomy. It underscored a fundamental truth in the search for cosmic truth, that the greatest interference often comes from ourselves. It reinforced the absolute necessity of rigorous local monitoring and taught a generation of scientists to maintain a healthy skepticism, even in the face of the most promising data. After such a definitive clearing of the air, the stage was set for a signal that was unambiguously real, a cosmic event so profound it would not only be heard across the universe, but witnessed in a spectacular flash of light. That ghost in the machine, the Peryton, was finally laid to rest by a microwave oven, a humbling reminder of how easily we can fool ourselves. But then came a signal that left no room for doubt. On April 28, 2020, the cosmos delivered a masterclass in clarity. A cataclysm erupted inside our own galactic neighborhood. A highly magnetized neutron star, known as SHGr02+14a had been restless for days, spitting out minor X-ray sputters. Then it screamed. A blast of X-rays and gamma rays detected by satellites like NASA, Swift, and Fermi erupted from the object. At the exact same moment, radio telescopes across the globe, including the Canadian CHIME array, recorded a tremendously powerful fast radio burst. This event, FRB 200428, was the historic breakthrough astronomers had dreamed of for over a decade. For the first time ever, a fast radio burst was caught in the act, and it was definitively linked to a known celestial object, a Magnetar, right here in our own galaxy. The connection was the smoking gun. Magnetars are the collapsed cores of dead stars, but they are unlike any neutron star you can imagine. They possess magnetic fields so powerful they could erase a credit card from hundreds of thousands of miles away. The energy released in this single event from our local magnetar was staggering. In radio waves, it was 1,000,000 times brighter than any outburst ever seen from a galactic magnetar before. Yet, in a crucial twist, it was also 1,000 times weaker than the faintest fast radio burst ever detected from another galaxy. This precise measurement was a golden gift. It bridged the immense energy gap between local phenomena and the cosmic monsters we see in the distant universe. It proved that the engines for at least some of these mysterious signals were indeed magnetars, but it also suggested that the extragalactic bursts must be produced by magnetars operating at their absolute, unimaginable limit, or perhaps by even more exotic processes. Astrophysicist Chris Bochenek called it a Rosetta Stone event. Suddenly, we had a translation manual. By studying this local, nearby eruption, we could finally understand the fundamental physics at work. The leading theory points to a starquake, a sudden cracking of the magnetar's incredibly dense crust, or a violent reconnection of its magnetic field lines like a cosmic short circuit. These events can unleash a firestorm of radiation across the entire electromagnetic spectrum, from X-rays to radio waves, exactly as observed. This single detection confirmed a viable mechanism for these cosmic enigmas. But it likely does not explain every type of fast radio burst. The universe, it seems, has more than one way to shout into the void. With one major piece of the puzzle firmly locked into place, our search shifts from these violent, momentary shouts to something far more subtle and pervasive. A signal that is not a burst at all, but a steady, unnerving hum that seems to emanate from the very dawn of time. But the universe's most profound signal is not a fleeting shout. It is a constant, quiet whisper left over from creation itself. This is the cosmic microwave background radiation, the ancient afterglow of the Big Bang. For decades, it was considered the ultimate proof of a hot, dense beginning, a nearly uniform sea of microwave light that fills every corner of the cosmos. Yet, as our maps of this primordial glow became exquisitely detailed, thanks to satellites like Planck and WMAP, scientists began to notice something deeply unsettling. The universe's first light is not perfectly smooth. It contains subtle irregularities, tiny variations in temperature that are the seeds of all future structure, the galaxies and clusters we see today. But some of these features are not so subtle. They are strange, large-scale anomalies that defy our most basic assumptions. One of the most puzzling is nicknamed the axis of evil. It is not a malevolent force but a startling alignment. The hot and cold spots in the cosmic microwave background are not scattered randomly across the sky. On the largest scales, they seem to be aligned along a particular preferred direction, a cosmic axis. This is a direct challenge to the cosmological principle, the foundational idea that the universe, on average, should look the same in every direction. There should be no special axis, no up or down, no left or right in the grand scheme of things. The existence of this alignment suggests that either our place in the universe is strangely privileged, or that our understanding of its fundamental geometry is profoundly incomplete. Then there is the cold spot. This is a vast, circular region in the southern sky that is significantly colder than the surrounding background. It is not just a statistical fluke. Researchers like Paolo Natoli and the entire Planck collaboration have confirmed its reality, ruling out instrumental error. So what could cause such a colossal chill? One breathtaking theory proposes it is a cosmic bruise, the imprint of a collision with another universe in the vast multiverse. The idea is that the gravitational tug of a neighboring cosmos during inflation could have drained energy from that patch of sky, leaving it forever colder. More conventional explanations point to a supervoid, an immense emptiness in space where a lack of galaxies means less energy, creating a shadow on the microwave background. Yet, searches for such a void have been inconclusive, leaving the exotic multiverse hypothesis tantalizingly on the table. These cosmic microwave background anomalies are the universe's oldest puzzles. They are not active signals but fossilized imprints from a time before time. They force cosmologists to confront an uncomfortable truth. Our standard model of the cosmos, for all its predictive power, might be a local rulebook, not the complete universal law. The very first light we can see is telling us that there is something fundamental we are missing, perhaps about the violent inflationary expansion that shaped everything. As we ponder these ancient whispers from the dawn of time, a modern signal demands our attention, one that behaves not like a fossil or a random burst, but with the precise regularity of a ticking clock. While the cosmic microwave background is a fossilized whisper from the beginning of everything, a star 1,500 light-years away began to behave in a way that felt almost personal. Its name is KIC 8462852, but the world came to know it as Tabby star, discovered by astronomer Tabitha Boyajian. This seemingly ordinary star in the constellation Cygnus became the center of one of the greatest modern astronomical mysteries, all because of its strange and dramatic flickers. Data from the Kepler Space Telescope revealed that Tabby's star did not behave like other stars. It underwent wild, irregular dimming events, with its brightness sometimes plummeting by an astonishing 22%. This was not the gentle, rhythmic dip caused by an orbiting planet. A planet, even a giant one, would only block about 1% of a star's light. This was something else entirely, as if vast, unseen shapes were drifting in front of the star. The light curves were bizarre, showing everything from sharp, sudden drops in brightness that lasted for days to long, shallow declines that stretched on for years. The strangeness ignited a firestorm of speculation. The scientific community scrambled for plausible explanations. Could it be a massive, chaotic swarm of comets stirred up by a passing star? Or perhaps a thick cloud of circumstellar dust unevenly orbiting the star? But the most captivating and controversial hypothesis was that of an alien megastructure. The idea was that an advanced civilization might be building a Dyson sphere, a vast array of energy-collecting panels encircling the star, and we were witnessing the construction process with different sections blocking the light at different times. For a while, the possibility hung in the air, a thrilling thought that captured the public imagination. Years of intense follow-up observations, led by Boyajian and a global team of astronomers, have slowly peeled back the layers of the mystery. Detailed analysis of how the star dimmed across different colors of light provided the crucial clue. If solid, opaque objects like megastructure panels were causing the dimming, they would block all wavelengths of light equally. But the data showed something different. The dimming was much more pronounced in blue light than in red and infrared light. This is the classic fingerprint of dust. Tiny dust particles are very efficient at scattering blue light, making the star appear redder when they pass in front of it, just like our sun appears red at sunset due to dust in our own atmosphere. This evidence strongly points to a natural, if extraordinarily complex, astrophysical origin. The leading theory now suggests a broken-up planet or a family of exocomets is orbiting the star in a chaotic, clumpy disk, creating an ever-shifting veil of fine dust that causes the unpredictable dimming. The true legacy of Tabby's star is not just the slow resolution of a puzzle, but the way it was solved. It was citizen scientists, volunteers sifting through public Kepler data as part of the Planet Hunters project, who first flagged the star's bizarre behavior. Their discovery highlighted that in our age of vast data sets, anyone with curiosity and an internet connection can help uncover the universe's deepest secrets. This star taught us that our galaxy is filled with phenomena we are only beginning to understand, where nature's complexity can so easily mimic the artifacts of intelligence. But what about a signal that is not about something blocking the light, but about a precise, repeating radio pulse that seems to have no star attached to it at all? The promise of a living world can be intoxicating. In 2007, the astronomy community buzzed with the discovery of Gliese 581c, a planet orbiting within the habitable zone of its dim red sun. Here, for the first time, was a world with the potential for liquid water, a rocky planet that could, in theory, cradle life. The excitement was palpable. Then came the signal. A team using the colossal Rattan 600 radio telescope in Russia reported a curious emission. It was a strong, narrow-band signal, precisely the kind of sharp, artificial spike that theorists predicted an advanced civilization might produce. It appeared to originate from the general direction of the Gliese 581 system. For a breathtaking moment, the pieces seemed to fit together perfectly. A potentially habitable planet, and now a whisper from that very neighborhood. Media outlets around the globe erupted with sensational headlines, proclaiming that we might have finally received our cosmic hello. The public imagination was set ablaze, yet within the scientific community, the reaction was far more measured and deeply skeptical. Veteran SETI researchers pointed to a critical flaw. The signal had been detected in only a single beam of the massive Rattan telescope. It was never heard again, and perhaps most damningly, it was never confirmed by any other radio observatory on Earth. In the rigorous world of signal detection, a one-time event from a single instrument is not proof. It is a candidate, and a weak one at that, vulnerable to a multitude of more mundane explanations. The most likely culprit, as further analysis soon suggested, was simple radio frequency interference. Our own planet is drowning in a sea of artificial transmissions. A broadcast from a passing satellite or a piece of ground-based equipment could have easily been reflected or picked up by the sensitive telescope, mimicking a cosmic call. The Gliese 581c episode became a textbook case of a premature announcement. It highlighted the immense challenge of separating a true interstellar signal from the cacophony of our own technological noise. This cautionary tale underscores the gold standard in the search for extraterrestrial intelligence, independent, repeatable verification. The entire process, from the initial thrill to the sobering letdown, serves as a vital drill, hardening our methods against the seduction of a false positive. It reminds us that the path to a genuine discovery is paved with disciplined skepticism. After such a clear lesson in managing our expectations, we are forced to look beyond radio waves altogether, to a mystery written not in electromagnetic code, but in the ghostly passage of a fundamental particle that should not exist. High above the frozen expanse of Antarctica, a balloon carrying a sensitive antenna drifted on the thin winds, listening for whispers from the cosmos. The ANITA experiment was built to catch the faint radio pulses generated when ultra-high energy neutrinos, ghostly particles with almost no mass, interact with the Antarctic ice. But it heard something that should not exist. On two separate occasions, it detected signals characteristic of a specific type of neutrino, the tau neutrino, but with a trajectory that defied physics. These particles appeared to be coming up from the Earth below. For a tau neutrino at such immense energy, this was a physical impossibility. According to our best models, neutrinos of that power should be completely absorbed after traveling through just a few hundred miles of rock. For one to emerge after a journey through nearly 8,000 miles of our planet's dense core would be like a bullet passing through a mountain unscathed. The implications sent a shockwave through the physics community. If these detections were real, they meant that our understanding of the neutrino itself was fundamentally flawed. One compelling, if exotic, explanation is the sterile neutrino. This is a hypothetical particle that interacts with ordinary matter only through gravity, making it a compelling candidate for dark matter. The theory suggests that the high-energy tau neutrinos detected by ANITA could have oscillated or transformed into these sterile neutrinos mid-journey. As sterile neutrinos, they would pass through the entire Earth unimpeded before transforming back into detectable tau neutrinos just as they exited the ice. Another, even more speculative, idea posits that the signal was not from a neutrino at all, but from the decay of a supersymmetric particle, a relic from the very early universe that decayed within the Earth itself. Of course, the scientific process demands skepticism. Many researchers have argued that the signals could be mundane reflections, glitches caused by cosmic ray showers in the atmosphere creating a radio echo that fooled the detectors. Yet, despite years of intense debate and reanalysis, no single conventional explanation has fully laid the anomaly to rest. The ANITA events remain a stubborn crack in the foundation of the standard model of particle physics, a hint that entirely new laws and particles are waiting to be discovered in the most unexpected data. While these ghostly particles challenge our understanding of the very small, another signal uses the fabric of the cosmos itself to map the impossibly large. These cosmic lighthouses offer a rhythm so precise it rivals our best atomic clocks. Pulsars are the spinning cores of dead stars, beaming radiation across space with a regularity that feels almost mechanical. Yet even this great cosmic clockwork sometimes stutters. Astronomers observe sudden, tiny jumps in a pulsar's spin rate, events known as glitches. These are not malfunctions, but profound messages from the heart of an object so dense that a single teaspoon of its material would weigh billions of tons on Earth. The Vela pulsar is a notorious offender, regularly hiccuping with a sudden spin-up before gradually settling back into its normal rhythm over weeks or months. What could cause such a predictable object to suddenly jump? The leading theory points to the star's bizarre interior. A neutron star is thought to have a solid crust of iron nuclei floating on a quantum ocean of superfluid neutrons. This superfluid can rotate without friction, but it occasionally becomes pinned to the solid crust. As the crust slowly spins down over time, the superfluid lags behind, building up rotational stress. Then, in an instant, this superfluid unpins and transfers its immense momentum to the crust, like a pot of water suddenly sloshing against its sides, giving the entire star a brief, measurable speed boost. These events are our only window into matter under such extreme pressure, a natural laboratory for physics that we could never recreate. By studying the glitch and the long recovery that follows, scientists like Andrew Lyne can map the star's internal structure, probing the very equation of state that dictates whether such an object remains a neutron star or continues its collapse into a black hole. The precision of these cosmic beacons goes far beyond their own internal drama. By monitoring networks of millisecond pulsars across the galaxy, astronomers are creating a gravitational wave detector on an unimaginable scale. The subtle stretching and squeezing of spacetime by passing gravitational waves should minutely alter the arrival times of these pulses, allowing us to listen for the faint ripples from the mergers of supermassive black holes. These lighthouses are not just objects of study, they are tools for testing the very fabric of reality. But for every signal that ticks with such reliable order, the universe has another that is born from pure, untamed chaos, a single, explosive event from a galaxy torn apart by its own violent history. Some of the universe's most spectacular fireworks are born from pure chaos. Far beyond our local galactic neighborhood, nearly 2.5 billion light-years from Earth, lies a celestial object of breathtaking beauty and violence. It is known as a collisional ring galaxy, a rare and stunning structure formed when one galaxy plunges directly through the heart of another, like a stone dropped into a still pond. The gravitational shockwave sends vast waves of gas and dust rushing outward, triggering a frenzy of new star formation in a brilliant, expanding ring. It is from the tumultuous heart of such a place, a galaxy designated FRB 20201124a, that a powerful fast radio burst erupted. This was not a random location. The discovery forged a direct and compelling link between these enigmatic signals and the most extreme, dynamic environments the cosmos has to offer. The narrative became clear. The cataclysmic violence of a galactic merger provides the perfect recipe for creating the engines of fast radio bursts. The collision compresses immense clouds of gas, igniting the rapid birth of countless massive stars. These stars live fast and die young, collapsing into the very objects thought to power these bursts. The environment around this FRB was scrutinized and found to be rich in heavy metals and seething with a strong, wildly fluctuating magnetic field. These are the exact conditions astronomers predict are ideal for forging magnetars. When a massive star born from this chaotic nursery reaches the end of its short life, it can collapse into a highly magnetized neutron star, an engine perfectly capable of unleashing the catastrophic energy of a fast radio burst. The burst itself carried further clues imprinted on its signal. It exhibited complex and rapidly changing polarization, a property that describes the orientation of its light waves. This twisting and turning of the signal's polarization is a telltale sign that it traveled through a turbulent, magnetized plasma. It fought its way through a storm of charged particles, which could be the remnant of the stellar nursery that formed the Magnetar, or perhaps the swirling debris still settling from the galactic collision itself. This single detection provides a powerful new directive in the hunt for the origins of these signals. It suggests we should train our telescopes on galaxies in the throes of dramatic transformation, on stellar systems that are actively being forged and reshaped by immense gravitational forces. The message is that fast radio bursts are not just random accidents, but the brilliant, fleeting signatures of cosmic construction sites. Yet if these brilliant flashes are the birth cries from stellar nurseries, what are we to make of a signal that emerges from the opposite end of the cosmic life cycle, a whisper from a time before the first stars were even born? While the cosmos blazes with the violent death of stars, a far quieter signal holds the key to its birth. This is the hunt for the 21-centimeter line from the cosmic dawn, the moment the universe woke up from its dark ages. After the Big Bang's initial fireball faded to a cold, dark sea of neutral hydrogen gas, the very first stars and galaxies began to ignite. Their intense ultraviolet light started to heat that primordial fog, a pivotal process that would eventually clear the cosmic haze and make the universe transparent. We can detect an echo of that transformation. The spinning of hydrogen atoms causes them to naturally emit and absorb radio waves at a very specific wavelength, 21 centimeters. By the time that ancient light reaches us, it is stretched into the meter band, a faint whisper from over 13 billion years ago. Astronomers predicted they would see a distinctive dip in the radio spectrum at that frequency, an absorption shadow cast by that early hydrogen as it soaked up the even more ancient light of the cosmic microwave background. Finding this dip would be like discovering a fossilized recording of the universe's first sunrise. The challenge is almost beyond comprehension. This primordial signal is incredibly faint, and it is buried beneath a roar of radio static from our own galaxy and countless other modern sources. It is like trying to hear a single, quiet note played in a symphony hall from the parking lot during a thunderstorm. In 2018, a small ground-based instrument called EDGES made an announcement that sent shockwaves through cosmology. The project reported a deep absorption profile that looked exactly like the predicted signal, but with a startling intensity. The dip was far deeper than any model had forecast. This implied that the primordial hydrogen gas was much, much colder than anyone thought possible. How could it have cooled so efficiently in the early, dense universe? The only plausible explanation seemed to involve something exotic cooling the gas. Theorists proposed that this something was dark matter. The idea is that the invisible dark matter particles, which vastly outnumber normal matter, were interacting with the hydrogen gas through a subtle force beyond gravity, siphoning away its heat and leaving it in a state of profound chill. If confirmed, this would be the first ever detection of dark matter interacting with normal matter in any way other than through gravity, a monumental breakthrough. Yet, the result remains intensely controversial. The difficulty of separating the signal from galactic foregrounds is immense, and many scientists worry that the EDGES team may have underestimated a subtle instrumental effect or a tricky source of interference. The quest to confirm or refute this signal is now a primary driver for the next generation of radio telescopes, most notably the Square Kilometre Array. This vast international observatory, with its thousands of antennas across 2 continents, will have the sheer sensitivity and resolution to peer into that ancient epoch and finally listen to the universe's first stirrings without the overwhelming noise. The pursuit of this primordial whisper takes us from the very edges of theoretical physics to a modern enigma that feels unnervingly crafted. A sequence of pulses that some argued could not be anything but a deliberate message. Humanity has not only listened, but it has also shouted back. In 1974, astronomers used the immense Arecibo radio telescope to send a deliberate message into the void, aimed at a distant star cluster 25,000 light-years away. This was not a random broadcast, but a carefully crafted pictorial transmission containing the essential ingredients of our existence. It depicted our solar system, the double helix structure of human DNA, the chemical formula for the building blocks of life, and a simple stick figure of a human being. It was a 3-minute-long shout, a cosmic postcard announcing, "We are here." Decades later, a strange echo seemed to return, not from the stars but from an English field. A crop circle formation appeared that mirrored the precise bitmap pattern of the Arecibo message. Yet, the data was altered. It showed a different solar system with an additional world, and the human figure was replaced by a larger being with a bulbous head, implying a silicon-based biology. For a brief, thrilling moment, it seemed like a response. The mystery was short-lived, as hoaxers eventually claimed responsibility for the elaborate prank. But the episode ignited a profound discussion that transcended the forgery. How would we actually recognize a reply? The Arecibo message was built on the assumption that mathematics and fundamental science are universal languages. An alien civilization, however, might perceive reality through a completely different sensory or cognitive lens. Their message might not be a neat bitmap, but a complex code based on quantum states, gravitational waves, or a principle of physics we have not yet discovered. Decoding it would be the ultimate challenge, forcing us to confront our own cultural and scientific biases. The original transmission remains a vital benchmark, a perfect example of what an intentional, information-rich signal from an advanced civilization should look like. It is narrowband, patterned, and packed with complex data structured in its very form. This entire thought experiment shifts the search from mere detection to interpretation, from hearing a signal to understanding its meaning. It asks us what we would do if the cosmos finally answered, not with a simple tone, but with a library of information. From this vision of a crowded, communicative cosmos, we must confront a signal that is the exact opposite, a profound and unsettling silence that speaks volumes. This profound quiet is a mystery in itself. We gaze at a galaxy filled with hundreds of billions of stars, many with planets orbiting in their habitable zones, where conditions seem ripe for life to spark. The numbers alone suggest a cosmos teeming with activity, a cosmic cacophony of voices. Yet when we listen, we are met with a deep and unnerving silence. This contradiction is the heart of the Fermi paradox, a simple question with devastating implications. Where is everybody? The silence we hear is a signal all its own, and it is perhaps the most perplexing one of all. Why does a universe so vast and so old appear so empty? One chilling answer is the Great Filter hypothesis. This idea suggests that somewhere between the emergence of life and the development of a galaxy-spanning civilization, there exists a barrier, an evolutionary or technological challenge that is almost impossible to overcome. This filter could lie in our past. Perhaps the jump from simple chemistry to self-replicating life is astronomically rare, making us a singular miracle. Or it could wait for us in the future. Maybe every advanced civilization eventually creates the technology for its own destruction, or succumbs to a resource collapse, or awakens some unseen danger we have yet to encounter. The silence would then be a grave warning. Other explanations are less grim but equally mind-bending. Perhaps intelligent life is common, but it is simply too alien for us to recognize. Their thoughts, their technology, their very mode of existence might be so different from our own that we are like ants trying to comprehend the internet, completely unaware of the conversation happening all around us. They might communicate using gravitational waves or quantum entanglement, technologies that are entirely invisible to our radio telescopes. Or they might be observing us from a distance, choosing a policy of cosmic non-interference, a galactic zoo where we are the unaware inhabitants. Another possibility is one of timing. The universe is 13.8 billion years old, and our technological civilization is little more than a century old. We are a fleeting spark in an unimaginably long cosmic night. Other civilizations may have risen, flourished for millennia, and vanished long before we ever looked up at the stars. Or our own era of listening may be just a brief window before we too transition to a different, quieter form of technology, disappearing from the radio spectrum and joining the great silence ourselves. This overarching absence forces a humbling perspective. It reminds us that every tantalizing signal we do detect must be weighed against this immense backdrop of nothing. It asks us to scrutinize each burst and each whisper not just for what it is, but for what its existence implies about the cosmos's habitability and the fate of intelligence. And so, against this canvas of profound quiet, a recent event shattered the stillness with coordinated brilliance, a burst detected by an unprecedented number of telescopes all at once. The silence was shattered by a chorus of electronic ears. In early 2020, a repeating fast radio burst designated FRB 2020-0120E did not just flash in the dark, it rang an alarm that was answered across the planet. For the first time, a global network of radio telescopes, from the deep space stations in Europe to the massive dishes in America, caught the same repeating source almost in unison. This was not a solitary observation. It was a coordinated scientific strike, capturing a flood of data that would transform a single point of light into a detailed portrait. The wealth of information allowed for a feat of cosmic triangulation of breathtaking accuracy. the signal was pinned down not to a vague patch of sky, but to a specific and utterly surprising home. It originated within a globular cluster orbiting the beautiful spiral galaxy M81, a mere 11.7 million light-years away. This proximity made it the closest fast radio burst ever discovered, right in our cosmic backyard. Its location was a profound shock to the astronomical community. Globular clusters are ancient relics, densely packed collections of stars that are billions of years old, where the furious pace of star formation ceased eons ago. The prevailing theory insisted that fast radio bursts were the tantrums of young, massive stars dying violently in active stellar nurseries. An ancient, quiet globular cluster was the last place anyone expected to find such a vibrant, energetic object. The mystery only deepened with the data's exquisite detail. The bursts themselves were passed down to timescales of microseconds, revealing incredibly short, sharp sub-pulses within the main flash. This microscopic structure was a crucial clue. The brevity of these sub-bursts means the region producing them must be incredibly small, likely no larger than a single kilometer across. That scale points directly to the surface or magnetosphere of a neutron star, an object where physics is pushed to its absolute limit. How could such a young, violent engine exist in such an old neighborhood? The answer, proposed by teams like the one led by Franz Kirsten, rewrites the life story of magnetars. It suggests these highly magnetized neutron stars can form in these ancient environments through alternative cosmic pathways. Perhaps the slow, steady accretion of material from a binary partner star pushes a white dwarf over its mass limit, causing it to collapse not into a typical neutron star, but directly into a magnetar. Or maybe two white dwarfs merge in a silent, cataclysmic embrace, their combined mass sparking into a magnetar born from the quiet death of old stars. This discovery shattered a single, simple narrative, proving that the universe has multiple ways to forge these incredible engines. The global campaign to study this one repeater was a masterclass in modern collaboration. It showed how a shared mystery can unite the world's instruments, turning a fleeting flash into a rich, multi-perspective dataset that forces our theories to evolve or be discarded. From this well-mapped signal in our local universe, our search must now stretch back across an almost unimaginable gulf of time to a whisper that has been traveling for half the age of the cosmos itself. That ancient flash emerged from a time when the cosmos itself was still in its youth. In June of 2022, the Australian Square Kilometre Array Pathfinder captured a fast radio burst designated FRB 2022-0610A. This was not just another burst, it was a time traveler. Follow-up observations with the Very Large Telescope in Chile pinpointed its origin to a group of distant galaxies locked in a slow gravitational dance. The light from this cataclysm had been journeying toward us for so long that we see the universe as it was just 5 billion years after the Big Bang. This makes it the most distant and ancient fast radio burst ever witnessed, a relic from a formative era of cosmic history. Its immense journey is the key to its scientific power. As the signal traveled across billions of light years, it passed through the sparse, ionized gas that filaments the space between galaxies, a structure known as the cosmic web. The longer the journey, the more this gas leaves its fingerprint on the signal, stretching it in a measurable way. This burst, having traveled farther than any other of its kind, carried the most pronounced dispersion signature ever recorded. It was a perfect probe for one of cosmology's most stubborn problems, the missing baryons. Theoretical models of the Big Bang predict a certain amount of ordinary matter should exist in the universe, but for decades, our inventories of stars and galaxies came up short. Where was the rest of it? The analysis of this ancient burst provided a definitive answer. The missing matter is not missing at all. It is simply hiding in the form of a diffuse, hot plasma that floats in the vast voids between galaxy clusters, a warm, hot intergalactic medium that is nearly impossible to see directly. The dispersion of FRB 2022-0610 confirmed that this elusive web of gas accounts for the exact amount of matter that was unaccounted for, finally solving the puzzle. Beyond its role as a cosmic measuring tape, this detection carries another profound implication. The fact that such a powerful burst occurred when the universe was only a third of its current age proves that the conditions to create these events, likely the birth or death of magnetars, were already in place. The universe was already capable of such spectacular violence relatively early in its history. This single flash from the deep past illuminates not only the invisible architecture of the cosmos, but also the persistent, dynamic nature of its stellar life cycles. As we use these brilliant flashes to map the present-day universe, we must also confront a far more subtle and enduring signal, a steady, all-sky glow that has puzzled astronomers for generations. Scattered throughout the galaxy is a ghostly signature written in heat. For decades, telescopes sensitive to infrared light have detected a faint, pervasive glow, a set of distinct emission bands that appear in nebulas around dying stars and in the vast emptiness between solar systems. These are the unidentified infrared emission bands, and they are a cosmic fingerprint with no clear owner. The light they emit comes at very specific wavelengths, a pattern that should act like a barcode, instantly identifying the molecule that created it. Yet, after all this time, no known substance, no single atom or simple molecule, matches the pattern perfectly. It is as if the entire galaxy is filled with a substance we can detect everywhere but cannot name. The leading suspect is a class of large, carbon-based molecules known as polycyclic aromatic hydrocarbons. Imagine them as tiny, flat flakes, like microscopic patches of chicken wire made from carbon and hydrogen atoms. These PAHs are thought to be common in space, vibrating with the heat they absorb from starlight and re-radiating it as this specific infrared glow. They are essentially the soot of the universe, the complex organic dust that fills the voids. But the case is not so simple. No single type of PAH, nor even a neat family of them, can explain all the variations in the data. The bands shift in intensity and precise position from one cosmic environment to another. This suggests we are not looking at one molecule, but a diverse population of carbon compounds, a cosmic zoo of complex chemistry. It could be a mixture of different PAHs, or perhaps something more exotic, like tiny carbon cages known as fullerenes, or even fragments of graphene. The presence of these bands is profoundly significant. They are tracers of complex organic chemistry, the very kind of chemistry that serves as the foundation for life. Where we see this infrared glow, we are witnessing cosmic factories churning out the building blocks of planets and, potentially, biology itself. Solving this mystery would do more than just put a name to a component of interstellar dust. It would illuminate the cosmic life cycle of carbon, showing us how this essential element is forged in stars, processed in space, and ultimately delivered to new worlds. It is a search for the chemical instructions that the universe scatters among the stars, and while this cryptic signature is written in the warm glow of complex molecules, another signal fills the cosmos with a very different kind of message, a faint, steady hum that has no known source at all. This all-pervading glow is the light of cosmic history itself. Spread thinly across the void is the extragalactic background light, a faint sea of photons that has been traveling for billions of years. This is not the light from any single star or galaxy, but the accumulated glow of every star that has ever shone. the combined energy output from all stellar furnaces since the dawn of time. It is the universe's total fossil record of star formation, a diffuse background hum of all the light ever created. Seeing this light directly is one of astronomy's greatest challenges. From our vantage point, it is utterly drowned out by brighter, closer sources. The zodiacal light from dust in our own solar system and the overwhelming glare of the Milky Way create a foreground fog that obscures this ancient, universal glow. Isolating the signal is like trying to hear a single, quiet conversation in a stadium filled with roaring crowds. So how do we measure the unseeable? Astronomers use cosmic probes, turning to the most violent objects in the universe for help. They observe distant blazars, galaxies with supermassive black holes that fire jets of radiation directly toward Earth. These jets produce incredibly high-energy gamma rays. As these gamma rays travel across the universe toward us, they have a chance encounter with the photons of the extragalactic background light. When a high-energy gamma ray collides with a background photon, they annihilate each other, transforming into a pair of particles, an electron and a positron. This process acts like a cosmic dimmer switch. The further a gamma ray has to travel through this sea of light, the more likely it is to be absorbed. By measuring how much the gamma ray flux from a distant blazar has been attenuated, scientists can work backwards to calculate the density of the extragalactic background light that it traveled through. It is like figuring out how foggy a road is by how dim a car's headlights appear from a distance. These meticulous measurements have largely confirmed our broad understanding of cosmic star formation, but they have also revealed a tantalizing tension. Some observations suggest the background light is more intense than our best models predict. There seems to be extra light in the universe. This could point to an earlier or more prolific population of the first stars, whose brilliant, short lives added more light to the cosmic total than we anticipated. Or it might hint at other, more exotic sources contributing to this universal glow. The precise measurement of this background is crucial because it acts as a ledger for the universe's total energy budget, constraining how galaxies have evolved over billions of years. This gentle, all-encompassing glow of accumulated history stands in absolute contrast to the next signal, a single, localized outburst of raw power so immense it defies belief. Sometimes the most violent events in the cosmos announce themselves not just with light, but with a ghostly particle. In April 2019, telescopes caught the brilliant flare of a star being torn apart. A supermassive black hole lurking in the heart of a distant galaxy had reached out with its immense gravity and shredded a sun that wandered too close. This cataclysm, known as a tidal disruption event and catalogued as at 2019 DSG, produced a beacon of light visible across the universe, but its true message arrived months later in the form of a single, high-energy neutrino detected by the Ice Cube Observatory, a vast telescope buried deep in the Antarctic ice. This ghostly particle, a neutrino with an energy millions of times greater than those produced in particle colliders on Earth, had traveled for billions of light years. Its arrival about 150 days after the flare's peak was no coincidence. It was a cosmic bullet fired from the heart of the destruction. The correlation, confirmed in 2021, was a monumental breakthrough. It proved for the first time that the chaotic maelstrom around a feeding black hole can act as a natural particle accelerator of almost unimaginable power. Theorists believe that as the stellar debris swirls into an accretion disk, powerful magnetic fields can launch jets or outflows. Within these relativistic jets, protons or other particles can be accelerated to nearly the speed of light. When these particles collide, they can produce high-energy neutrinos which, unlike charged particles, travel in straight lines, unaffected by magnetic fields, pointing directly back to their source. This single detection solved a long-standing mystery, identifying at least one source of the astrophysical neutrinos that constantly rain down on Earth. But its significance runs even deeper. This was a triumph of multi-messenger astronomy, the practice of observing the same event using different cosmic signals. By combining the story told by light with the message carried by a particle, we gained a more complete picture of the physics at work than either could provide alone. We learned that particle acceleration in these events is not instantaneous, but a sustained process that continues long after the initial optical flash. This one observation links the invisible world of particle physics directly to the dramatic death of a star, revealing that black holes are not just destroyers, but powerful engines that can forge the most energetic particles in the universe. Having journeyed through 23 of the cosmos' most mysterious signals, from the solitary wow to this coordinated shout of light and matter, we are left with a profound new perspective. Each signal, whether a burst, a whisper, or a particle, is a piece of a grander puzzle. They tell us that the universe is not a quiet, static museum, but a dynamic and often violent arena, filled with engines of immense power and complexity that we are only beginning to understand. These discoveries are not endpoints but gateways. They highlight the incredible power of coordinated observation, of listening with every tool at our disposal, from radio dishes to ice-bound sensors. The greatest lesson may be that the cosmos is constantly speaking to us in a language of energy, particles, and gravity. Our task is to keep building better ears, to keep learning how to listen, and to remain forever curious about the next mysterious signal waiting to be decoded. From the ghostly imprint of the Big Bang to the recent, precise triangulation of a galactic flash, these 23 signals paint a universe of breathtaking diversity and constant conversation. They are not random noise, but a symphony of cosmic processes, each instrument playing its own part. The brief, energetic whispers of fast radio bursts tell us about the violent deaths and births of stars. The steady hum of background radiation maps the large-scale structure of everything. The perplexing alignment of the cosmic microwave background challenges our most fundamental assumptions about the cosmos itself. A common thread binds these discoveries together, a revolution in how we listen. The lone astronomer reviewing data printouts has been joined by global armies of collaborators. A single baffling event like the wow signal might remain a mystery forever if it happened today, but not because we would ignore it. It would trigger an instantaneous alert, swinging radio dishes from Chile to China toward its coordinates, while optical telescopes and X-ray observatories in space join the hunt, all within minutes. This is the power of multi-messenger astronomy. We are no longer just listening to the universe, we are observing it in stereo, combining the distinct songs of light, radio waves, and ghostly particles to hear the full composition. This coordinated effort transforms anomalies into precise data points. A fast radio burst is no longer just a mystery, it is a tool for weighing the invisible matter between galaxies. A single neutrino from a devoured star confirms that black holes are the most powerful particle accelerators in existence. Each signal acts as a natural laboratory, allowing us to probe the behavior of matter under gravitational forces and magnetic fields so intense we could never hope to recreate them. This relentless search is a lesson in cosmic humility. For every mystery we solve, like the terrestrial origin of the Perytons, two more profound questions emerge from the data. The confirmation that magnetars cause some fast radio bursts immediately begs the question of what causes the others. The entire journey underscores a fundamental truth. the universe is not a quiet, static void, but a dynamic and often violent arena. We are learning that these signals are not mere curiosities. They are the very language of the cosmos, speaking to us of its composition, its history, and its ultimate fate. As we connect these disparate cosmic dots, a final, overarching picture begins to form, one that asks us to reconsider our own small place within this grand, chaotic, and beautiful tapestry. We have journeyed through a gallery of cosmic enigmas, from the solitary perfection of the WOW signal to the revolutionary multi-messenger events that link brilliant flashes of light to ghostly particles. Each of these 23 mysterious signals underscores a fundamental and humbling truth. The universe is not a quiet, static museum. It is a dynamic and often violently unpredictable arena, a place where our current understanding, for all its impressive power, is merely a starting point. Every solved mystery peels back a single layer, only to reveal a deeper, more complex question waiting beneath. This relentless pursuit is what drives us forward. It fuels breathtaking technological innovation, from telescopes that see the entire sky at once to sensors buried deep in Antarctic ice. It forges powerful international collaborations, uniting scientists across the globe in a shared quest for meaning. Most importantly, it cultivates a profound appreciation for the sheer complexity and beauty of the cosmos. These unsolved puzzles are not failures of science. They are its very heart, reminding us that the greatest adventures lie not in the answers we already possess, but in the questions we have yet to even formulate. Let these cosmic whispers inspire you. The next time you look up at the night sky, see it not as a silent void, but as a canvas alive with possibility. Support the scientific endeavors, both large and small, that strive to decode the universe's deepest secrets. The next great discovery, the signal that will rewrite our textbooks and reshape our cosmic perspective, could be traveling toward us at this very moment. It is just a signal away, waiting for the right moment to be heard. So stay curious, keep exploring, and never lose the sense of wonder that first made you look up.